Good afternoon, everybody. I'm Doug Sillers with AT&T. Thanks, everybody, for coming out this afternoon. Today, I'm going to talk a little bit about optimizing mobile applications, and specifically Android applications. To start off, AT&T at our Developer Summit on Monday, we launched a tool called the Application Resource Optimizer, or ARROW. And the whole point of ARROW is we don't want this to happen to you. This is a review from the Android market. Battery killer. Slow. It uses way too much CPU and kills the battery. It's a great idea, but poor execution. Optimizing your mobile app should not have to be a hard thing to do. So we've launched the Application Resource Optimizer. We call it ARROW. So I'm going to talk through a few things here. We're going to start off with some AT&T research and best practices, and then go into how the ARROW tool works, show you some of the results and some of the feedback we've gotten from developers we've been working with over the last year, and then finally show you as a developer how you can use ARROW to optimize your mobile application. So ARROW came out of the AT&T research labs in New Jersey, and they developed a prototype, and they brought it to the developer program at AT&T so that we could begin doing outreach with developers. And what they discovered is simple design principles to your mobile app can optimize the network connectivity. It can shorten the connection time. It reduces the number of connections. And when you reduce the amount of radio usage that you're using, you save the battery. You also lower the server loads on your back-end servers, and resulting can end up speeding up your mobile application. One thing that's important about building a mobile app is you have to understand that a mobile network is very different than your regular PC application. When you have a normal PC application, you're connected directly to the internet. When you have a mobile applications, there's a wireless state machine that exists in the RAN of a carrier's network, and that makes the way you treat your connections to the network, you have to treat them very differently than you would in a traditional PC setting. And so what we see now is even in the best-in-class applications out there for mobile, they're not considering that uniqueness, and they're actually being very inefficient with the way they use the radio. So what we're hoping is that tomorrow, people will start using tools like ARROW to optimize their mobile apps to improve the user experience and improve the network efficiency. So what is a state machine? And this is a state machine for the 3G network. Every single mobile network has a state machine. There are three states in the 3G UMTS state machine. You have idle, DCH, and fetch. It's a triangle. When you're in idle mode, the radio's off. When the radio's off, you can't connect, but you're also not draining the battery. To make the connection to DCH, there's a 2-second delay. And there's a delay in all mobile networks, and that's just strictly your phone talking to the tower. And that connection takes some time. It can be up to 2 seconds before that connection occurs, before you can form a TCP connection to the internet. Because there's that 2-second delay, we keep the radio on after all the packets are sent. And so you stay up in DCH, which is high bandwidth. You can send a lot of data back and forth. It's also draining your battery a lot. So you stay in that state. There's a tail time of 5 seconds. You stay up in the DCH mode in case more data comes through to avoid that 2-second delay. If nothing happens, you go into a shared state. It's called fetch, which is a little bit lower energy. It can still allow some signaling packets through. Your radio's still open, but it's a lower bandwidth, but it's also lower battery power. So we're kind of always balancing the difference between draining the battery and keeping a radio connection open. After 12 seconds in fetch, you go back down to idle. What's important about this is if you send down a giant 3-megabyte video, you have this tail time of 5 seconds and then 12 seconds. But if you send a 2-byte signaling load, you also have 17 seconds of radio time where the radio is on, which can be a huge battery drain if that happens over and over and over during your application. So, through all of these. So as you have these, if you have all these small connections sending small amounts of data, use up a lot of battery life because the radio's on for 15 seconds after every connection. All right. What we've discovered in reaching out to a lot of the top developers is that developers are really worried about building their app and the IP layer of their application. Traditionally, carriers, we've been very worried about working on optimizing our RAN, our network, and optimizing the devices. but no one's really been paying attention to the cross-layer interactions, and that's the state machine. And what's important is the state machine traffic triggers the state transitions, and those state transitions directly affect the battery life, the user experience, and the wireless efficiency of your mobile application. So let's go through some of the best practices that we came across. Caching, network connections, how you handle the network connections, whether they're periodic, managing multiple connections, closing your connections in an efficient manner is something we see a lot. Using the peripherals also drains the battery. If you leave the GPS on for 45 minutes, you can just watch the battery life go down, right? We've seen applications that don't have failovers. Just simple things. We've come up with a lot of best practices. It's at developer.att.com/ARO/best practices. I'm going to walk through a couple of them. This is a major news organization. We looked at their mobile application, and there's a lot of duplicate content. We see images sent down 8, 3, 7 times. And then finally at the bottom, in 5 minutes, the weather was downloaded 11 times. The weather file's 45K. 11 times 45K, you're about half a megabyte of weather data downloaded. If they'd implemented a cache, it would have been downloaded once. There's no delay in the page rendering because you're waiting for this 45K XML file to download before the page renders. Another example is managing the connections. This is another news application. This is a view from our arrow tool. And what you see here in the top row is the throughput. I'll laser over there as well. It's showing how much data is coming through. The next line, you can't really see it, but these are the packets coming up, the packets going down. We're measuring network traces here. We group the bursts into different colors. This is the way I think of this, is looking at the forest instead of looking at the trees. It just helps us mentally look around the issues. We calculate the user input. In this line down here, this is key presses on the phone. And this is a simulation of the RRC state machine, how much energy is being drained while this is happening. Well, what's happening during this trace? At the beginning, there's a key press to start the app. The app starts, and then the news and the stocks and everything are downloaded. And then there's a delay of about 10 seconds. And then we have these 3 pink bursts, and those are all images being downloaded with delays in between each one. And then finally, that last arrow is showing you when the home page of this app renders. It took 30 seconds from start to finish of the app starting up before the customer is able to see anything. Well, let's think about this. If we manage our connections and cut out all these dead areas where there are no packets going up and down, that's about 15 seconds. If this news organization were able to remove those 15 seconds of dead space, the app would appear to the customer to load twice as fast. Another example we see a lot is not closing the connections properly. So what's happening here? You go up to your server, you download a lot of data, and then the connection isn't closed properly. So the radio stays open, and then several seconds later, there's either the server or the client discovers the connection's still open, sends another message up to close the connection. It's delayed by 5, 10, sometimes 60 seconds, which keeps the radio on for a longer period of time. When you keep the radio on for a longer period of time, we see many applications, 10, 20% of the battery life from the radio is because people aren't closing their connections immediately. So we see this in 50% of all the apps that we tested. So it's a major issue. And it's a pretty simple fix. It's just close the connections when you're done with them. Go to the next one. This is one of those mobile content things that people have been talking about for years. We see lots of apps. This is my dog, Max. But we see a lot of websites, mobile sites, downloading giant files to show thumbnails. You know, we call them dumb nails. I thought it was a great term. But you know, if you send it down at a reasonable size for a mobile device, it loads in 3 seconds rather than 45 seconds. Obviously, that's a huge gain for your customers. It's a lot of server load off of your back end. Huge improvements for everybody. So you've seen some of the basic examples. Now what? So we have this arrow tool, and it's going to give you benchmarking on your mobile app. It gives you visibility and we've seen some examples of how the radio resources are being used, how the battery is being used. It's benchmarking your app against 12 best practices we've come up with. And it helps you as a developer actually discover optimization strategies for your application to make your app more efficient. So how does Arrow work? So you run a data collector on a handset, and then you run a test while the data collector is running. When you're done with it, you stop the data collector, and you have a bunch of files stored on the SD card, which you can transfer to your PC, where we have an analyzer that takes all that information and processes it, runs the simulations, and tells you some of the best practices, and gives you a whole lot of data analysis on your application. So we launched on Monday, and we've got 2 ways to collect a trace. It's available in the Android emulator. It's also, we have several devices specially set up with Arrow on a Keynote device anywhere. Here is an example of the data collector, and this is an app that I wrote. This is the view on the. When you run the data collector, it's recording all of the data traffic. It's looking at the TCP sessions. It's looking at the HTTP packets. It's collecting video at 3 frames per second of what's going on the screen. This is really useful, especially for me, in that if you run a trace and then look at it a couple hours later, you don't remember exactly what was going on. If you have video that's synced directly to your trace, it helps a great deal. It looks at all the user inputs. It measures the battery level, and it measures all of the peripherals that are being used, the GPS, the camera, the Bluetooth, etc. Then, when you're done, you take that over to the analyzer, and it's a Java Web Start application that shows the video over here, and then it shows you lots of information about your trace. It looks at all the data, and it gives you feedback based on the best practices we've come up with. It removes all the unknown. It applies the radio and the power models to your application, so you know exactly how the battery is being drained when your application is running. And then you can look through all the characteristics of the trace, and you can learn a lot about how your application is behaving. So here's some feedback and some results that we've gotten from developers. This is a messaging application we were looking at. And if we look, this is the trace from it. And you can see it's a very network-heavy application. When we measure the bursts, the color coding describes different types of bursts. And you can see there's a lot of pink bursts in there. Those are periodic bursts, things that happen over and over again, every 30 seconds, every 60 seconds. And in this trace, 56% of the radio energy were these periodic bursts. It was also, those periodic bursts were sending down the same file over and over and over again. 93% of the data being sent down was duplicate. And then finally, the blue, I don't know if you can see it on these slides, but those are delayed connections that weren't closed promptly. They weren't closing the connections. 21% of the energy is from those. So their initial fix, it doesn't look all that much different, but what they did is they reduced the energy of the periodic connections by 26%. They also reduced the amount of duplicate content by 43%. So it went from 93 to 50%. Pretty big improvement. No fix on the radio energy, but what they did here, they actually made no changes to their mobile app. They did it all on the server. What this is looking at is this is a table of the duplicate content that was sent down during the trace, and this is all in the Arrow tool. And the top graph is what was in the first trace, and the bottom graph is in the bottom one. You can't see it here, but you might see in the last column there are a lot more numbers. And that's because the first trace, every single one of those duplicate files was 18.5K. You can see in the second one, there are a lot smaller numbers because now it's 368 bytes. So obviously, if the duplicate file is now that much smaller, you reduce the amount of content coming down. For every 50,000 users, that's 9.5 gigabytes of data pulled off their server every single day. So then they made a bigger fix. As we recall, 56% of the radio energy was periodic connections, 93% of the content was duplicate, and 19% of the radio energy was because they weren't closing the connections promptly. On their next release, they completely removed the periodic connections. So that removed 56% of the radio energy, and it removed 93% of the data being trafficked because they removed all of the duplicate content. We're still working with them on the delayed connection closing. I was hoping to have a new slide for you today, but that's still in development. They're still working on that one. But let's look at the final messaging from this. They completely removed the periodic connections. The battery power savings, I gave you the number of how much data it was saving, but if you actually look at how much energy of battery savings it is, it's enough to power 20% of a house. every single day. So that's a lot of battery power being saved. Absolutely no duplicate content. The data usage in bytes was reduced by 80%. And the end result is the customers are happier. The app runs faster. They don't drain the battery as much. Their data plans don't get dinged as much. Here's an example of an application you've probably heard of. It's called Pandora. And at our keynote at our developer summit, we had Tom Conrad, the CTO of Pandora, talking about how they used Arrow. But the way Pandora works is you can see this large, dense group of packets going up and down. It's a song. So they're downloading a song to listen to. But then every 60 seconds, they were doing analytics. Is Doug still listening? Is Doug still listening? Makes for great analytics. However, if we look at the battery drain, those periodic connections was 43% of the battery, while the music was only 37%. So they're actually spending more battery power on the analytics than they actually were on the music. So Pandora really took this to heart, and we walked through a whole bunch of examples for them of how they could fix it. The first thing we suggested was go every 120 seconds, right? You half the amount of power that you're using because you're dinging less often. What they're actually doing is they're going to piggyback those onto the music files. Extra couple hundred bytes with every single music file. You don't even notice it in the energy profiling. But they reduce the amount of energy being used by the app by about 50%. So you as a customer now can listen to Pandora twice as long. So who's happy? Everybody's happy. So why do you need application optimization? Here's some folks who've used it. Pandora. Now that we better understand these interactions, we can optimize our application. We had some folks from Zynga at our developer summit as well. You will find that new offerings from Zynga will do much better with respect to battery and network usage. We worked with Yelp. I shared this work with the engineering team, and there was a lot of interest in the results. And then finally, we're AT&T. We have a lot of apps on our own. And so, of course, we're going to eat our own dog food. And so, quick note of thanks. We appreciate your assistance in helping improving our application. So Arrow, we've released it. How can you, as a developer, use it? Well, the data collector is available as it's a plug-in to the Android emulator. You can also use it directly on devices using Keynote or Device Anywhere. That's for Android. That's great. There are a lot of developers for other platforms. Can you use it as well? Yes. If you collect a PCAP file of your application running on one of those other platforms that we don't yet support, we can do the basic network-only analysis of your application. And then the data analyzer is available from the AT&T developer website. How much does it cost? It's free. We're competing with the Intel folks who are talking just before me, who are also offering their optimization for free. So go to developer.att.com/arrow. You can get the analyzer download, which is what interfaces with the emulator for running the traces. We've got user guides. We've got a lot of documentation on how to run tests, on how to do the analysis. We've got an FAQ. We've got forums. A lot of great information out there. And I have a few minutes left. Thank you. I have business cards. I'd be happy to talk with you afterwards. If you have any questions, I can take them now. Yes?
You mentioned one of your biggest best practices had to do with closure.
Yes.
What are some of the other major best practices?
Well, duplicate content is a huge one. So you saw a couple examples there where data is just being sent down over and over. One of the examples was a news app that sent down the weather. The weather had the correct cache headers to save it for 5 minutes, but the file was downloaded 11 times, which ended up being a half a megabyte of extra traffic, which, number one, dings the customer's data buckets. Number two, it enforces a delay in how quickly the page can render. If that file's cached and you're reading it from the internal cache, that's a lot faster than getting it from the device. We see a lot of inefficient connections. One of the things that Zynga said in terms of making their app more efficient is they didn't have a connection manager. So they were just kind of, I need some data, pinging the network. And so there was no organization to it. It was just, I need data. Let's contact the network. Whereas if they had bundled all of those transactions together, they were saving a lot of network efficiency. And so they've actually done that in many of their new apps. Yeah. Yes, so we're able to look at the packets. You can look at all the TCP connections and see all the files that were transferred and everything as well, yeah. Yes? So we are open sourcing it this summer. So we're in the process of going through open sourcing, so it'll be available for anyone. We do have a roadmap for this year as well. So we started with Android because you got to start somewhere. So, but again, if you collect a PCAP file, and from what I've seen, I've collected some with iThings, and using over Wi-Fi, and you can still do the same analysis because it's applying the radio resource state to the packet. So it's just all a simulation. So you can still get some of the same useful information. Yes. That you can actually run on a mobile device. I would like to get to there, yeah. For right now, it is only available on the device anywhere. Those are real devices, but it is not something that you can physically hold in your hand, right? Any other questions? Well, I appreciate you guys coming out. I know you had a choice of coming to the Aero Talk or seeing live boxing at the ESPN booth. And I really appreciate you coming to my talk. Thank you. If there are no more questions, thank you very much.